In this short demonstration, we will be showing how the 9640 can be used in the application of power sensor linearity calibration. This is a common measurement which is typically made over a wide dynamic range, particularly with some of the modern wide range sensors such as the diode sensors. This measurement would be made at maybe 5 or 6 steps over the range of the sensor, which could well require a range of 80 dBs of attenuation. And the traditional technique for making this measurement is to make use of calibrated step attenuators or fixed value coaxial attenuators. Now the 9640 in this case is being used to calibrate a 75 ohm sensor, and we're using a 75 ohm sensor to illustrate another feature of the 9640, which is its ability to work easily with a 75 ohm system. In addition to the standard 50 ohm sensor that is available for the 9640, an optional 75 ohm head is available, and that avoids the need to use an impedance converter from 50 ohm to 75 ohm. The attenuators are typically calibrated with pads in order to achieve a good match for their calibration and also a good match for their use. These typical value of pads here are 3 dB. Together with the loss of the matching pad gives us a total of around 10 dBs of loss that we must account for when considering the maximum output of the level generator that is required to provide a signal that is close to the top end of the range of the sensor from which we make our linearity tests. Now in the case of most signal generators, the output level is quite low at the 50 MHz test frequency that we're using here. However, the 9640 is capable of generating 18 dBms from its 75 ohm head. So the traditional measurement process will employ the calibrated attenuators, and they will be accompanied by a table of calibrated values and uncertainties, and we must take these calibrated values into account when making the calibration. However, by using the 9640 we simplify the process vastly by having an accurate output available directly at the output of the leveling head, presented directly to the input of the UUT, and we have a feature on the user interface that enables us to make a reading of the UUT error directly without the need for any calculations. So we will start the process at, in this case, a level of 10 dBms. We have a slight error from nominal, but I need to adjust that to read exactly 10 dBms because we are interested in linearity from that point. So I make a slight adjustment to the output, and now we read exactly 10 dBms. And I'm going to program a level step of 20 dBs, so I can step down by any number of 20 dB steps to explore the linearity of the sensor over this range. So now I'm going to decrement the output by a 20 dB step and another 20 dB step, so we've gone down by 40 dBs, and there is a very small error here. If I switch on the offset feature, I can now display that offset in terms of the UUT error, and in this case I am using now a percentage, so I can express that level error in percentage of power, or I can change that units to dB to express the level error in dBs, since in this case I'm working in dBm. So now we make an adjustment to the output until the power meter reads exactly correctly, and now I have an indication directly on the screen of the 9640 of the linearity error of the power meter. making a much simpler, faster and less error-prone measurement process. In some cases, this calibration might also be carried out at a high frequency, for example 1 gigahertz. And in that case we would go through exactly the same process. An advantage of using the 9640 is of course that it is calibrated also at that value of 1 gigahertz, and obtaining calibration of attenuators at higher frequency for our fixed or step attenuators might be more troublesome, or that calibration data may not be readily available in the calibration laboratory because they are typically only calibrated at a frequency of 50 megahertz. So we have a much simpler and more widely applicable process by making use of the 9640. And of course exactly the same process would apply if you are simply using the 50 ohm head for 50 ohm power sensor calibration.